Hello, and in this video we're going to be looking back at exponential models with base b. So we're going to still look at exponential models in base b, but in this case we're going to be looking at decay models. So the actual formula itself is the same. It's y equals a times b to the x, but in this case b is not going to be greater than 1. It's going to be between 0 and 1. Where a is the initial amount and b is going to be 1 minus the decay rates instead of 1 plus instead of adding the growth rate, we're going to subtract the decay rate from 1. So that's the change in the formula, is this number b is going to be less than 1. So we're going to apply this problem. This is one of the problems from your worksheets. It says population of the small town was 1,000 in 2001. And has been declining at a rate of 3% per year. So we would use this formula because it has a yearly rate, not a continuous rate. So a continuous rate has a different model, but in base B, that's because we have a yearly or hourly or per second rate, some kind of time increment for a rate. Okay, it says write a function to model this population and use it to calculate halving time for the population. Use the rule of 70 to check your answers to make sure they're reasonable. In what year will a population reach 250? Alright, so we don't have the rate. Well, we do have the rate. It's 3%. So that means that B is going to be 1 minus 0.03 for 3%, or that's going to be 0.97. So that's going to be your B value. A is going to be your initial population, which is the initial amount, which is 1,000. So your equation is going to be y equals 1,000 times 0.97 to the x power. So that's your model for this population. Now, if you're doing halving time, that means that you're going to be half as much. That means your population needs to go down to 500. If it starts at 1,000. So if we solve this equation for x, then we should get the time it takes to half this population. And we can double check that with the rule of 70, but let's figure this out first. So as always, we divide by the number in front of the base, which in this case is 1,000. And this makes sense. We have a half here equals 0.97 to the x power. Now it makes sense it's a half because it's halving time, so this should be a half. Alright, now our next step would be to take the log of both sides. Now it doesn't matter which log. Before I just use the regular common logarithm, but this time I'm just going to use ln. It should give me the same answer. 0.97 to the x power. Remember, the rule that we're using here is that the base comes down in front, or the power, the exponent comes down in front, becomes x times ln of 0.97 and is equal to ln of actually 0.5 for 1/2. So we're just going to divide by ln of 0.797 on both sides of the equation. So my answer for x is going to be approximately, let's see, ln of 0.5 divided by ln of 0.97, we get 22.76. 22.76. And what's our time in this problem again? Let's see, years. So about 23 years, between 22 and 23 years to make it be half the population to get to 500 people. Now let's just double check that with the rule of 70. So write it over here. rule of 70 states that we just need to take 70 divided by the p-value to get the years or the time. In this case, 70 divided by 3%, and 70 divided by 3 is 23 1/3, so we get 23.3 years here. So we're pretty close. It's an estimate in this case. We're pretty close to the same answer. Let's just verify that on our calculator as well. So we have 1,000.97 to the x power, and we want to graph when that's going to be equal 500. Okay, so our window has to go at least to 30 because we were saying the years is 22, so let's go out to a little bit bigger than that, 35. We'll go by 7 here. Now we don't need to go to 550,000. This was from the previous one. We're going to start out at 1,500 because it's going to go down in actuality. It starts at 1,000 and goes down, so we're going to go down by 500 here. So there'll be 3 marks. Let's look at the graph. It drops here. We're decaying, so it's going to drop down. So we're looking at when it's going to reach this marker right here, because that's the 500 mark right there. So hopefully that is going to be close to intersect 22.76. Enter for first curve, enter for second curve, take it close to 20.22, enter. So it looks like it's really close to the same answer we got here by the logarithm, 22.756, which is what we got here, but we're rounded up. So the rule of 70 was close. The calculator gave us a close approximation. Now it says, my final thing here is what year will it approximately reach 250? Well, let's use our same type of formula here, except that we're not halving again. I mean, we're cutting it in half again. So should the answer be 40? If we're cutting it in half again, this one was cutting it in half already and was 22.76. So is that going to be 44 or 45? Close to 45 years? Let's just verify that. That's I'm making a guess here, and that would be something I would do, make a guess or approximation to 250. But it looks like it drops down here pretty quick here. I don't know if it's going to get to 45 there. So let's do the actual formula. So it says 250 is our goal. We start out with 1,000.97 to the x power. So in the process, we can use our previous problem here and do the same thing. We're going to divide by 1,000. We're going to then take the ln. It looks like it's going to be very close to the same type of thing. If we divide by 1,000, we're going to get a fraction of 1/4 this time. So 1/4 equals 0.97 to the x power. And then we're going to take the natural log of both sides. Because that's what we did this time. Took the natural logarithm, bring this thing down in front. This exponent comes down in front. We get x ln of 0.97 equals ln of 1/4, which is 0.25 if we do a decimal there too. And so our answer here is going to be x is equal to ln 0.25 divided by ln 0.97, which is about, let's see what it is, it's about ln of 0.25 divided by ln 0.97. So 45, so my guess was pretty close. 45.5 was close to doubling that number. 45.5 years was our answer for doubling, or having it again. Basically, we had to cut it in half again, 250 people. So we're using this equation each time, and remember, this is used if we have a percentage per time, not a continuous one. Continuous one uses a different model. This is a percentage per time, and the base is 1 minus the decay rate. That's the difference between decay and growth. Growth is 1 plus, decay is 1 minus. All right, we'll finish up this discussion in the next video when we're going to do exponential decay models of base E.